So at the end of the last video, we brought up this important point that if a function was continuous at a point, if we knew it was continuous, then we already know that its limit is equal to its z-coordinate at that point. And this allows us to compute a lot of limits very, very quickly. We said that the two types of functions that we know are definitely going to be continuous everywhere they're defined is polynomial functions in two variables and rational functions in two variables. So notice how easy this is going to make actually attempting to compute limits in examples number 5 and 6 in certain cases. Take a look here. Example number 5, part A. Can I find this limit if it exists? Okay, well the first thing that I note is that we have a polynomial function. So I'll say note that f of xy is equal to x to the third times a y minus 2yx plus 3y squared minus x. This is a polynomial function. And since polynomial functions are continuous, that means that if I'm going to do the limit of x comma y as I approach negative 2 comma 2, that should be exactly the same. Let me write it like this. I'll put in my f of x comma y. That should be exactly the same as doing a, not even as doing a limit, but that should be the same as just doing f of negative 2, 2, right? Because the polynomial function is continuous. I'll even add that kind of up here. This is a polynomial function and is therefore continuous. So that means I can just evaluate this limit by just plugging in negative 2 and positive 2. So let's see, that would get me negative 2 to the third times a 2 minus 2 times a negative 2 plus here a 3 times a 2 squared and then minus a negative 2. So let's see, I think if I simplify all of that down, I'm going to get, what is that, like negative 16. I'm going to get plus in 8. Oops, I don't know why I wrote a y over there. This would just be a 2, so let's see, that's going to be like plus a 12 and then plus a 2. So it looks like here I have like 22 minus a 16, so that's just going to end up being 6. Boom, limit evaluated. Again, the only reason I can do that is because I know my function's continuous. If I didn't have continuity, I'm in trouble. Okay, take a look down here, part B. I should be able to find this limit super easily. I can again say, oops, swap that back. Note f of xy, which is equal to 2xy plus 1 over x squared plus y squared, is a rational function. And I'm going to make a note here that it is defined at 1 comma 1, which is what I'm approaching right now. There's no conflict with 1 comma 1. It looks like the only problem that this function could have had would have been at 0, 0. That would have made the denominator 0. But at 1, 1, everything's fine. And so I know that then this function is continuous at 1 comma 1. So again, if I want to do the limit here of my f of xy as I'm approaching 1, 1, this is the same thing as just going to my function and plugging in 1, 1. So this should be super simple. I'm just going to get, let's see, 2 times 1 times 1 plus 1 over 1 squared plus 1 squared. So this is going to be, what, 3 over 2. Done. So again, continuous functions are awesome, but you got to make sure you have a continuous function. If you don't have a continuous function, I can't go ahead and do a direct substitution. So notice, could we have used this above strategy to find the limit as I approach 0, 0? That answer would automatically be no. No, I can't do that because the function here isn't actually defined at 0, 0. So I could not have just tried to plug in 0, 0. Okay. Let's take a look here at part C. Is my function continuous at 0, 0? Okay, well, if I mean, it seems like I can't plug in 0, 0 to evaluate the limit, but let's see maybe what happens if I try to justify if this function is continuous. So remember that in order to show that a function is continuous at 0, 0, or at any point, you would have to show that the limit comes out equal to the y value, or the z value. So let's go ahead and try to show that. Okay, so let's see. I'll say note g of 0, 0 is, let's see, if I try to plug 0, 0 in here, I'm going to get 0, or what is that, 1 divided by 0? This is going to be undefined, right? Well, if that's the case, then there's actually no way at all that I could have the limit as xy approaches 0, 0 of g of xy. There's no way I could have that come out equal to g of 0, 0, because g of 0, 0 doesn't even have an answer. Okay? This automatically means that g of xy is not continuous at 0, 0. All right, let's take a look here at example 6 as well. In fact, I'm going to ask you to pause the video right now and try to read through example 6 and give it a shot on your own. And once you're done, you kind of think you have some answers, try to unpause the video and you'll see me go through the solution. All right, so hopefully you did spend some time taking a look at this question. It's important to try to experiment and test your understanding, as you're kind of going through some of these things. So let's see here. Example 6, part A. Is this function continuous at 0, 0? Well, notice here that what I would have to try to do is first test again what the y value or the z value is and compare that to the limit. So I could say note f of 0, 0 is undefined. So kind of like what we had set up above, there is absolutely then no way that the limit here could be equal to f of 0, 0. So I can definitely say that f of xy is not continuous at 0, 0. That's almost a carbon copy of what we had seen back in part C. But now take a look at part B. I'm going to redefine the function here and do a piecewise function. I'm going to say, okay. Let's imagine we're going to use the top formula every time that x comma y is not 0, 0, and we will use the bottom formula whenever x, y is 0, 0. So this kind of tells you what formula you use to get your z coordinate. All right, well, let's see what happens here. Again, I can go ahead and note some things. I could say if I wanted to plug 0, 0 into my function, I first have to recognize I have to use the bottom formula to do it. The bottom formula says no matter what you plug in, you always get an answer of 0. Sounds good. Okay. Well, now what I would have to do to check continuity is see what the limit is going to be as I approach 0, 0. But actually, we already kind of have done something similar to this. Notice that if I'm approaching 0, 0, that means that on my surface, I am dealing with whatever point is kind of directly above my origin, right? So like this is kind of the spot on the surface that I'm approaching here, but I'm not at that point. Remember that we said that when we think about what's happening, we're thinking about kind of like having circles around our point and then slowly shrinking the size of our circles as we kind of get closer and closer and closer. So that's what's happening with the limit. I'm using those circles and I'm shrinking in or pinching in on this point. So if that's what I'm doing, then when I go ahead and I take my limit here, and I do my limit, I have to say that my circles that I'm using are going to be existing on this top portion of the function, because those are all the points on the circle the points on the circle are all not at or not above 0, 0. They're all other places. So the z coordinates for those points on the circle are calculated using this other formula. But this is a limit we already computed a few examples back, and we saw that this limit was going to be equal to 0. We could do that by simply factoring the top and simplifying and canceling some stuff out. So notice in this case, we now have that the limit and the y value are equal. So I can say that since the limit of g of xy as x comma y approaches 0, 0 is equal to g of 0, 0 So since this happens, then g of xy is continuous at 0, 0. What kind of happened here is a really interesting sort of idea. What happened here is that apparently on our picture, there must have been initially a hole right above where 0, 0 was. And that would have made the function discontinuous in general. Like if I went back to over here, that would have made the function discontinuous. But we kind of added in an extra point that essentially plugged the hole and made everything nice and connected. You probably had seen examples like this back in a Calc 1 class where you had holes in functions. And sometimes you would have a dot that was like down here. But if the dot was kind of just moved to be at exactly the right height, then you could have filled the hole and made the function all nice and connected. The same sort of thing is happening with this piecewise function, but now on this surface.